Good morning and welcome. Energy transition is a crucial issue nowadays, and we need methodologies and tools for assessing and tracking its evolution. Today we are going to present to you a framework for the sustainability assessment in the energy transition environment. The current energy paradigm is dominated by fossil fuels, more than 80% of the total primary energy supply, and it is responsible for the greenhouse gases emission, with severe environmental drawbacks in terms of climate change and air pollution, which impacts negatively on the people's health, and large part of those pollutants are due to the energy sector. In terms of social equity, energy consumption is unevenly distributed across the world, and this is maybe due to technological or infrastructural gaps or affordability issues. Fossil fuels may also be relevant for the energy security. Some countries, like the European Union, highly dependent on fossil fuel imports, are relying on the reserves located in politically unstable countries.
The concept of sustainability is at the heart of the energy transition. Sustainability has been defined as development that meets the needs of the present without compromising the ability of future generations to meet their own needs. The evolution towards sustainability implies several transitions, including the energy transition, social and cultural transitions, as well as a transition of the economy. This is not meant to be a state of equilibrium, but rather an evolutionary trajectory, and we need holistic and integrated visions, approaches and tools.
Sustainability is a multi-dimension issue. Besides the environmental sustainability, which of course is crucial for the survival of the humankind, other dimensions have to be considered, such as the efficiency in the energy exploitation, the economic and social aspects.
Three out of 17 Sustainable Development Goals of the United Nations are about energy systems evolution. Goal number 7 focuses on affordable clean energy for all. Goal number 11 emphasizes on resilient and sustainable cities. And goal number 13 ensures actions to combat climate change. Well, for successful assessment of these goals, we need a multidimensional view and also an integrated analytical framework based on quantitative indices.
As has been mentioned by my colleagues before, the sustainability is a multidimensional development. Too much emphasis on the environmental perspective could endanger the future sustainability and eventually jeopardizes the development of the energy transition as well. Therefore, we need a holistic approach for assessing the progress of sustainability to make sure that all the involved dimensions could be developed harmonically. The proposed sustainability assessment framework considers the interplay of different dimensions: economy, energy, environment, and society. Each of them can be further assessed by a set of KPIs. However, those dimensions are not always supporting each other. For example, focusing on the economy development may cause environmental damages. Enlarging the natural reserves may shrink the development of the nearby communities. Further, when the problem comes to how important one KPI is over the others, the judgment is sometimes subjective and arbitrary. Thus, we need eventually to consider both numbers and words into the assessment and make sure the opinions from the decision makers are consistent over all aspects as well. In this paper, we use the multi-criterion decision-making approach to construct the assessment framework.
For a given country, the assessment of the sustainability in each analyzed scenario is performed through the definition of different key performance indicators for each of the four considered dimensions: economic, energy, environmental, and social. All the KPIs are mapped with respect to the SDGs and are thus used for quantifying the evolution over time towards the targets that the SDGs set.
The analytical hierarchy process, aka AHP, is adopted in this paper. AHP commonly involves several steps. First, construct the problem as a hierarchy, expressed in terms of criteria, subcriteria, and alternatives. The pairwise comparison are then performed over criteria and subcriteria. Consistency check is then performed to assure the opinions are not inconsistent. Finally, relative weights from both the comparison matrices and quantitative matrices are used to obtain the final results. Following the AHP steps, we regard the assessment problem as the goal to rank different scenarios. Then the importance of the considered four dimensions and their included KPIs are evaluated one over the other on a scale of 1 to 10 to form the comparison matrices. The relative weights of each matrix is obtained by getting the eigenvector of the largest eigenvalue of each matrix, by comparison the largest eigenvalue of the matrix and the average of the maximum eigenvalue of, say, 100,000 random matrices of the same dimension. The consistency of the pairwise comparison can be determined. As the KPIs used to describe the scenarios are numerical, we use linear functions to turn them into pairwise comparison automatically. Finally, after getting all the relative weights, we can obtain the final scores of each scenario.
We have developed a software to plan the installation of photovoltaic generators and wind turbines. Thanks to our long-term research on this field, it is possible to simulate the hourly profiles of generation with respect to the electricity consumption and compute the indicators of energy balance.
The common aspect in the modeling of PV and wind power generation is the reduction of the conversion efficiency at partial load. The installation of many tens of gigawatts of photovoltaic and wind power plants requires remarkable terrain surfaces. As a consequence, it is very important to accurately assess the land occupancy. The land occupancy of PV system is higher in building integration rather than in ground-mounted application, due to the presence of many obstacles in the roof zone. In general, the land occupancy of wind farms is higher than in case of PV system. We have an elementary cell within the center the wind turbine that is surrounded by other 4 elementary cells with the other 4 wind turbines.
The RESPLAT platform allows to analyze in an integrated way and from an energy planning perspective the multidimensional impacts of the exploitation of renewable energy sources, with particular reference to wind and solar PV. It couples an originally developed database, fed by data automatically taken from different datasets, a calculation kernel using several function libraries and algorithms written in Python language, and a web interface with a backend section developed in Django REST framework and a front-end based on the JavaScript React library. Besides environmental parameters like global irradiation, air temperature and wind speed, various topographic data like urbanization, terrain roughness, altitude and presence of desert areas are considered, allowing for a pre-screening of the analyzed territory through the definition of different suitability criteria for the selected areas, according to the type of technology to be installed. The database currently stores more than 10 terabytes of data, and the included areas are growing to eventually contain 87 countries from North Africa, Europe, Middle East, Russia, China and other Asian countries. The platform permits to assess the exploitable renewables potential and to evaluate at different territorial scales and with an hourly time granularity the energy producibility of various technological solutions, and to quantify the related financial impacts and environmental effects.
Egypt is an area of the world with a low consumption per capita and a high dependence of fossil fuels, which export is relevant for the national GDP. So, energy transition is challenging, both from the economical and the technical point of view. The case study implements the proposed sustainability assessment framework by comparing different scenarios with a focus on the electricity generation. Three scenarios have been built. They are the results of the coupling of two electricity demand scenarios and other two electricity generation scenarios. Regarding the demand scenarios, we have a reference load or an high electrification case. Regarding the generation, we have the low penetration of renewable energy sources or a high penetration of renewable energy sources. Productivity from RES is calculated, then energy balances are performed with an hourly basis. The figure shows an example of a day with the comparison of generation loads, the storage charge and discharge, and the calculation of surplus and deficit. The energy balances are calculated for Egypt from 2022 to 2040. Each scenario considers a particular evolution of electricity consumption, electrification rate, of loads, etc. Thus, each scenario leads to a different evolution in the portfolio of plants, in terms of tens of gigawatt PV generators and wind farms.
The key performance indicators mentioned in the description of the proposed methodological approach and related to the four main dimensions considered, economic, energy, environmental and social, have been calculated for all the three scenarios over the whole time horizon, from 2022 to 2040. These KPIs have been then used in the analytical hierarchy process for assessing and comparing the evolutive sustainability trajectories of the three scenarios.
As can be seen from the criteria and sub-criteria results, we consider each dimension equally important to the sustainability assessment. However, under each of them, there are some KPIs dominant the others. For example, in the environmental dimension, CO2 emissions is the dominant one over the other considered factors. As for the simulated scenarios, we can see from the graph that stronger sustainability policies leads to a more effective evolution to the achievement of the sustainability. All the scenarios see an acceleration only after 2030 due to the inertia of the energy systems, but stronger sustainability energy policy have a higher speed. When talking about the individual scenario, S2 reaches a higher sustainable development than S1 along the time horizons, as well as the final point due to a higher RES contribution in the generation mix, while S3 has even higher achievements due to an extra electrification compared with other scenarios. From the assessment results, it is clear that our proposed framework and model can evaluate the path towards sustainability considering various aspects, both words and numbers, even conflicting ones.
The current energy transition seems not suitable to ensure the survival of humankind, and the shift from fossil fuels to renewable energy is surely needed. Designing trajectories for a shift of the paradigm in the energy sector is a multi-dimensional problem. It is not only an issue of sustainability in terms of environmental impacts, but involves societal aspects at large, with a focus on socio-economic issues, including social equity and energy security. Policy and action in the transition arena may be coherent or conflicting with the goals set for different dimensions. Consistent frameworks like the one developed in this paper and based on multi-criteria decision analysis are needed to track the transition trajectories in a multi-dimension perspective and with a quantitative assessment. The framework proved to be effective when applied to the case study of Egypt, a kind of significant country due to both its high dependence on fossil fuels and their impacts on socio-economic welfare.